Have you ever seen one of those huge cargo ships and just wondered, what is going on inside that thing? It's so easy to just see it as a giant steel box, right? But it's so much more than that. You should really think of it as a floating city, a city that's totally self-contained, with its own power plant, its own kind of circulatory system of pipes, and its own waste management system. It's incredible.
So, you look at this, and yeah, it looks like absolute chaos. It's this wild, tangled web of pipes for fuel, for cooling, for compressed air, for you name it. But believe it or not, there's a beautiful logic to all of it. So today, we're going to untangle this web by thinking of the ship as a living, breathing creature. We'll start with its machinery, its all-important cooling systems, and the fuel that keeps it all alive.
All right, so here's the plan. We'll kick things off with our living systems idea. Then we're going to listen to the engine's heartbeat, see how it stays cool, follow the fuel that feeds it, and finally look at how this giant manages its environmental footprint. Okay, so to wrap our heads around this maze of pipes and machinery, we're going to use a really powerful metaphor. Just imagine the ship isn't a machine at all. Imagine it's a living organism with its own set of organs and its own circulatory system. You know, this way of thinking is a game changer. The engine, that's the powerful beating heart. And all those thousands of meters of pipes, well, those are the arteries and veins. They're circulating fuel, water, air, lubricants, literally everything this thing needs to stay alive out on the open ocean. It turns a confusing diagram into a real story of survival.
So, let's start with that heart. We're diving right into the diesel generator system, or what the pros call the DG system. This is the absolute power core of the ship. It provides the electricity for everything, and I mean everything, on board, from the navigation equipment right down to the kitchen lights.
And here it is. You can see the main parts laid out. Notice there are two big generators, DG1 and DG2. That's all about redundancy. It's an absolutely critical design choice when you're hundreds of miles from anywhere. If one fails, the other kicks in. And all those lines going in and out, yep, those are the arteries and veins we were just talking about. Let's follow a few of them.
First up, the most important one, FO, fuel oil. On our diagram, you can see it in brown. This is the lifeblood. It's the raw energy that the diesel engine chomps through to create mechanical force, which the generator then magically turns into electricity. Simple as that.
Now, see those blue lines? They're labeled LT and HD, which stands for low and high temperature cooling. An engine this massive generates a staggering amount of heat. So this cooling system works just like your own body's circulatory system, constantly pulling that destructive heat away from the engine's guts to stop it from, well, melting down. No cooling, no power. It's that critical.
And keeping this giant metal heart from overheating is a serious engineering puzzle. I mean, you're literally surrounded by an endless supply of cold water. So how do you use it? Well, it turns out there are two main ways to think about it.
On the left, you've got the direct approach. It's called an open loop. It just sucks in cold seawater, runs it through the hot parts, and then spits the now warm water back out. Simple, but kind of risky. On the right is the more clever system, a closed loop. It's just like the radiator in your car. It uses its own clean fresh water to cool the engine. And then, here's the trick, it uses seawater to cool that fresh water in a totally separate step. And this right here is a classic engineering trade-off. Do you go with this simple open loop? I mean, fewer parts means fewer things can break, but the massive risk is corrosion. Salt water eats metal for breakfast. Or do you go for the more complex closed loop? Yeah, it's got more parts, but it keeps that nasty, corrosive salt far away from your very expensive engine, making it last way longer. It's a constant battle between simplicity and protection.
Okay, so our engine's got power and it's staying nice and cool. Awesome. But none of that matters if it runs out of food, right? So now we have to look at how it gets fed. We're going to trace the incredible journey of fuel all the way from the huge storage tanks buried deep in the ship up to the engine itself.
Now, designing a fuel system isn't something you do on a whim. There are super strict rules. For one, it has to be flexible, able to burn both the cheap, thick, sludgy, heavy fuel oil for long trips and the cleaner marine diesel oil, which you need to get the engine started when it's cold. And you see that point about interconnected pumps? There's that word again, redundancy. If one pump dies, another one is ready to take over in a heartbeat. Out at sea, reliability is everything.
That heavy fuel oil, it's got a ton of energy, but man, is it dirty. It has to be cleaned like crazy before it gets anywhere near the engine. So the fuel gets pushed through a whole series of filters, each one finer than the last. It starts with a coarse mesh, then goes down to a 20-micron filter, and finally it's forced through a 5-micron filter. Now to put that in perspective, a single human hair is about 70 microns thick. That's how pure the fuel has to be to avoid wrecking the engine's super-sensitive injectors.
So here we can see that whole journey. It starts in the bunker tank, gets pumped through heaters, because this heavy stuff is basically asphalt at room temperature, and then it's shot into purifiers that literally spin the water and sludge right out of it. Finally, a little device called a viscosity regulator makes sure the fuel is the perfect thickness for a clean burn right before it hits the engine. Every single piece in this chain is a critical, carefully considered design choice. Okay, so you have this incredibly powerful engine running 24/7, burning thousands of gallons of fuel. It's going to make a mess. It's going to produce waste. And when your backyard is the entire ocean, dealing with that waste isn't just a nice thing to do. It's the law. It's governed by really strict international regulations.
And it all comes down to this. In any engine room, you're going to have little leaks of oil, lubricants, and water. It all collects at the very bottom of the ship in what's called the bilge. Now, you can't just pump that oily mess overboard. A huge international agreement called MARPOL, that's short for marine pollution, has very, very clear rules against doing that.
And this is the clever system that makes compliance possible. The bilge system basically acts like the ship's liver. It collects all that oily water from different spots into a holding tank. Then, it sends it to a special separator that does exactly what it sounds like. It separates the oil from the water. The nasty oil gets stored to be disposed of in port, and only the clean water goes overboard.
So how clean does that water have to be? Well, MARPOL measures it in parts per million, or ppm. If you discharge water with less than 15 parts of oil per million parts of water, you're good to go. It's so clean, you won't even see a shimmer on the surface. But anything over 100 ppm, that's totally prohibited because it'll leave a nasty, polluting oil slick.
And what's really cool is how these environmental laws directly shape the ship's design. This is the actual formula engineers use to figure out how big the bilge pump needs to be. You just take the diameter of the main bilge pipe, here it's 125 millimeters, plug it into the rule, and boom, it spits out the required pump capacity. It's a straight line from international law right down to a specific piece of hardware.
So you see, pretty much every system on a modern ship is a delicate balancing act. It's this constant tug of war between the demand for massive power and the deep responsibility to protect the ocean.
And that kind of leaves us with a big question, doesn't it? For over 100 years, we've been perfecting these systems to squeeze every last drop of power out of fossil fuels. But now, as we're all looking toward a more sustainable future, the challenge is just massive. What's it going to take? What new tech, what new fuels, what new rules will we need to totally re-engineer the heart of these amazing machines for a truly sustainable future at sea?